Okay, we're going to continue our lectures on numerical integration. That's what we did the last time. If you recall, we looked at the trapezoidal rule, but I'm just going to go back and revisit that last example we didn't quite have a chance to get through properly in the last lecture. Okay, so to recap, what we're trying to do when we're integrating in engineering is, in some sense, to take the mean of something. Now, normally, when we think about the mean of a set of values, we have a finite number of different values, we add them up, we divide by the number of values, and that gives us what you might term a discrete mean. Okay, you have a finite number of things and you just average them. An integral is a similar kind of a thing, except now you're doing it in some kind of continuous sense. So you're integrating over a range from here to here, and you're not entirely taking the mean. You'd need to actually divide by the interval width to calculate the mean, but there's a very, very similar, close correspondence between taking the mean of a set of values and taking an integral. When it comes to doing anything with computational methods, you can't normally do things in a continuous way. You have to break things back up into discrete things. So even though we might be trying to calculate the mean or the integral of a function, we saw when we had a look at the trapezoidal rule, we actually have to break it up into discrete elements again. Okay, so in a sense, it's almost like going from the continuous back to the discrete. So when we looked at the trapezoidal rule last time, we looked at what the error looked like, and we saw that it looked like the width of the interval cubed multiplied by some second derivative type term, which then suggests that if the second derivative of the function you're trying to integrate is 0, you'll get the exact answer. And of course, the only function for which the second derivative is 0 everywhere is a straight line. So the trapezoidal rule does a really great job of integrating a straight line, but you don't really need a numerical method to do that, because you can just do it by hand. However, if you split up those intervals, split up that range into a number of different intervals, you can then make an approximation, and there'll be a little bit of error in each one of those approximations. So we saw that going from the trapezoidal rule, where we just use one big interval to cover our entire domain, to the composite trapezoidal rule, where we split up our domain into multiple segments and then do those little integrals in each one of them, approximately. The way in which we framed the composite trapezoidal rule is we assumed that each of the spaces, each of the widths of those little segments were uniform. Typically, we call that mesh spacing, or that size of the interval h. Okay. I also said, and we didn't really I went through this a little bit quickly, is that in actual fact, for the trapezoidal rule, those segments don't have to have uniform size. And in actual fact, if you've got some strange kind of function, maybe it sort of goes like this, you could take quite big intervals out here and you wouldn't get much error. But as you approach this really sharp, pointy bit here, you might want to take much, much finer intervals to make sure that you're picking up the way in which the function changes. Because if you just choose a point there and a point there, and like that, you're going to miss all of that area up the top there in your integral. So that width of that is really important. And we also saw that the error term was proportional to the second derivative, as I've already said. So you can see here that the second derivative is very high, so we would expect there to be significant error near this really sharp point. So let's just have a look. Okay, so that's one good reason why we might use unequal segments. The other is that often if we're taking experimental measurements for something, we can't necessarily guarantee to get all our data points at nice even intervals. If you're measuring something in time, then you probably can guarantee it. But maybe, for example, something is a function of the wind speed, and you're measuring something as a function of wind speed, and you can only measure it at whatever the wind speed is today. Okay, you can't get those things in nice equal order. So if you need to do an integration with respect to that, it's not going to be possible to have evenly spaced h. Okay, so that was the trapezoidal rule, and it's worthwhile just having a quick look at what the composite trapezoidal rule looks like. The integral, and this really should be an approximately equal to, because there's going to be an error in there. I should put the lights down. It's equal to the function value at the very left-hand side the function value at the very right-hand side plus the sum of all the function values in the middle multiplied by 2, multiplied by our width divided by 2. Okay, the composite trapezoidal rule for unequal segments, it's pretty straightforward to derive. What we do is we start with the integral that we're trying to solve, which goes from x1 to xn, where n is the number of points, or number of points that we've got. We split that up into n minus 1 segments, and in each one of those segments we then integrate from x1, or first point to the left point to the right point. So x1 to x2 in the first, x2 to x3 in the second, etc., all the way across to the right. So what we've done is we just split this integral into a sum of integrals, and for each one of those we use the trapezoidal rule. Okay, so this first one becomes x minus 2 minus x1, that's the space, the width of that interval, multiplied by half the function value at x1 and x2. So that's this term here is the trapezoidal rule applied to that mini integral there. Likewise, this one is the trapezoidal rule applied to that there, etc., etc., and finally that last one there is the trapezoidal rule applied to that. So we can see that if x2 minus x1 is the same as x3 minus x2 is the same as xn minus x minus 1, in other words, we do have a uniform mesh spacing, we can just write things, well, pretty much as we've got up the top here, taking this constant space out the front. But when we don't have evenly spaced intervals, we can't do this. Okay? And we've actually got to include the mesh spacing outside each part of the composite trapezoidal rule. Okay, so let's go back to our bungee jump, and we remember that quite a simple expression, dz dt is equal to v. Effectively, that's the definition of velocity. So if we integrate both sides of this with respect to time, that disappears. We just have z is equal to the integral of v dt, which is exactly what we've got there. For this particular case, if you recall from the previous lecture, there's actually an analytic solution, but we're going to integrate it numerically using the compound trapezoidal rule with unequal elements, just for the exercise. So this is what our velocity is as a function of time. That's given to us as a function, and we're going to choose these points in time. And we're going to say, well, we've got these velocity measurements at this particular time. Let's use this discrete data that we've measured experimentally and apply the non-equal trapezoidal rule to it. So what we've done here, well, in actual fact, this is an extremely simple little bit of code. There's our time, there's our velocity, and just for reference, the way in which this velocity information was given was we actually rounded up the analytic solution, rounded the analytic solution to the closest integer. Why did we do that? Well, it just gives you a feeling for the kind of thing you might expect in experimental data. You can never measure anything experimentally exactly. There's always going to be some kind of measurement error. This, even though it's a bit of a funny way of doing things, this approximates the kind of experimental error we might get in practice. So if we put these into this function here, and I'll talk about this in a second, integrate it forward, we actually get an estimate of the distance that the bungee jumpers travel is 231.7 metres. The actual analytic solution is 234.1. Now, it's not really sensible to compare these two answers because there are in actual fact two sources of error in this thing here. First of all, there's the error because we've actually rounded the exact solution, and we only did that to mimic experimental data, so there's definitely going to be some error, in fact a large amount of error as a result of that. Then there's going to be another little bit of error associated with application of the trapezoidal rule. Now, MATLAB actually has its own inbuilt trapezoidal rule integration. Okay, and it's a function called trapz, and you just pass in the x and the y, or the t and the v, or whatever things that you want to integrate. So this is the independent variable. That's the dependent variable. Sorry, wrong way around. Independent variable, dependent variable. Pass that into trapz, and that will do the non-uniform trapezoidal rule for you. Okay? Even though you'll need to code this up, it's also safe to know that you can actually just use this inbuilt MATLAB function. And in actual fact, you'll find that for nearly everything we do in this unit, there are MATLAB functions that will be able to do it for you as well. So while you're learning this stuff, you're learning this so you understand how these things work, so that you will know in future, when you actually come to doing some real problems, whether you should be using trap Z or whether you should be using something else. And you have an understanding of the methodology behind them all. Okay, so that's the kind of what we did last time in terms of the trapezoidal rule. We're going to move on today to some much better integration techniques. Okay, the first thing that we need to do is get you familiar with something that are called the Newton-Cotes formulas. And the Newton-Cotes formulas, in actual fact, the trapezoidal rule is the simplest Newton-Cotes formula. But there are other ones that are the most common ways of integrating functions. So the Newton-Cotes formulas, in fact, not generally, always, they're based on replacing a complicated function or some experimental data or whatever you've got with a polynomial that you can actually integrate analytically. So in effect, in the trapezoidal rule, that's what you're doing. You're fitting a straight line between 2 points that are on the curve, and you are calculating the integral under that straight line segment exactly analytically and saying that's an approximation to the real integral. Well, you don't actually have to fit straight lines. You can fit all kinds of different functions to it and, again, integrate those functions analytically. So all of these Newton-Cotes formulas are based on that general idea. So if we have a look at the table down here, and you should be able to see that. So if we have one segment, it means we have 2 points, and we have the trapezoidal rule. Okay, so we've already looked at the trapezoidal rule. It's b minus a, where b is the right-hand value, a is the left-hand value, times the function value. Well, this should really be function value at a and function value at b. It doesn't really matter. Divided by 2. So that's the trapezoidal rule, which we did last lecture. And across here is the truncation error. Simpson's rules. There's 2 Simpson's rules. There's Simpson's 1/3 rule and Simpson's 3/8 rule. We're going to look at both of those today. In Simpson's 1/3 rule, it takes 3 points. Therefore, you need 2 segments. So if you're going to do Simpson's rule, you've got some kind of function, you need 3 data points and 3 function values. And the formula for Simpson's rule is, again, if that's b and that's a, it's b minus a multiplied by 1/6 function value at the left plus the function value at the right times 4 times the function value in the middle. And we're defining now the step size here as being h between the 2 points. So for Simpson's rule, h is equal to b minus a on 2. Well, Simpson's 1/3 rule. Simpson's 3/8 rule, we're now going to use 3 segments with 4 points. So we add another one across there. So b now goes to there. We've got 4 points, 3 segments. Likewise, the rule is b minus a divided by 8 multiplied by that top thing there, the function values at either side, plus 3 times the sum of the function values in the middle. The truncation error for both of Simpson's rules looks a bit the same, although it is different. 1/90th h to the 5th. So previously with the trapezoidal rule we had h to the 3rd. H to the 5th multiplied by some 4th derivative term now. Likewise, for Simpson's 3/8 rule, we have something similar. The only thing that's really different is this coefficient. We've still got an h to the 5th, and we've still got a 4th derivative. So what this says, for both of these cases here, if the 4th derivative of the function that you're integrating is equal to 0, you can integrate it exactly. So in other words, both of Simpson's rules, the 1/3 and the 3/8, will exactly integrate a cubic polynomial. Okay? Boole's rule, which is the next one, we're not going to spend any time doing that, but it's the next order up, so it's dependent on the 6th derivative, and it's got a term that's proportional to h to the 7th. So we can see here that the error depends on that mesh spacing quite significantly. H cubed for trapezoidal, h to the 5th for Simpson's 2 rules, h to the 7th. So if we make the mesh spacing 2 times smaller, we expect the error in other words, you have to have more points, we expect the error to be 8 times smaller with the trapezoidal rule, 32 times smaller with Simpson's rules, 128 times smaller if you're going to use Boole's rule. Okay, so that idea that things get more accurate as you take smaller steps, there's a concept called the order of the method, and that order basically is that power there. This is a 7th order method, Simpson's rules a 5th order method, etc. Okay, so with the trapezoidal rule, just going back to a simple example, if we're integrating from A to B, the blue line here is the analytic function. These are the values that we've obtained either from a function call or perhaps they're experimental data. The composite trapezoidal rule, say we're going to use 4 points, 3 segments, is we do fit straight lines between each of them and then do the integrals in each of these things separately and add them up. We talked about the error there. We saw previously when we were using polyfit, when we had those points, that higher order polynomials tended to fit data better. There's something we need to talk about there, but tended to fit the data better because they had more ability to bend and twist. So a straight line can only be a straight line. A quadratic can only kind of like have a curvature in one direction. A cubic can have a curvature in a couple of different directions, etc. Now, there was, of course, a limit to that. If we keep on going to higher and higher order polynomials, you tend to get these big oscillations and wiggles. Okay, and my recommendation would be cubic's probably the highest order you want to get to. Maybe you could go to quartic depending on what you're doing. Okay, but we expect, if we're fitting a polynomial to data and then using that to integrate, we expect the higher order polynomials should give us better data because we hope that they will be a better representation of the underlying function. And that's the reason that Simpson's rules work, because they actually are. So let's have a look at the same function now. There's just got this one function here. It's the same on both sides. Simpson's 1/3 rule, we need 3 points. Simpson's 3/8 rule, we need 4 points. So what we're going to do, the blue curve here is the known function. In both cases, it's the same function. We're going to fit a parabola for Simpson's 1/3 rule, which goes through those points, and we're going to fit a cubic for Simpson's 3/8 rule to those data points, just those data points that we've got. And then we're going to analytically integrate, in this case, we're going to analytically integrate the quadratic, and here we're going to analytically integrate the cubic. And we don't actually do that, of course, because it turns out that there's a nice formula for these. We'll get to those in a minute. But effectively, that's what these two rules are doing. Okay, and so we then say the actual area under this curve is given by this, approximately given by this shaded region here, which is the area under the polynomial that we've just fitted. Okay. So the most important thing to take away from this is this first point here. The underlying concept of this is simple. You fit a polynomial to the data points and you analytically integrate the polynomial. And you say that that's a good approximation to the integral. That's all we're doing, and it's the same with the trapezoidal rule. Okay? The error will depend on those powers and those derivatives. Okay, so using second and third degree polynomials, we believe will help reduce our truncation error, and I think the examples we'll go through today, I hope will convince you of that. The rules for fitting a quadratic and a cubic are known as Simpson's rules, and those are the 1/3 and 3/8, and that's what we'll be focusing the rest of the lecture on. So, Simpson's 1/3 rule, and I have to say, this is probably the single most commonly used technique to integrate functions you will ever come across if you ever have to do any numerical work, at least in your undergraduate degree. It's usually sufficiently accurate that you'll get a pretty good result out of it. Okay, the results will depend on the mesh spacing that you take, but generally you can get some pretty good results out of it. So what we're going to do, to those 3 points that we've got, we're just going to look at one pair of intervals. We're going to fit a polynomial that looks like ax squared plus bx plus c. We don't know what the coefficients a, b and c are, And in actual fact, we never have to know this. Okay, but that's what we're going to do with Simpson's 1/3 rule. So we're going to say that the exact integral that we're trying to calculate, which is this thing here, is approximately equal to the integral from x1 to x3 of the integral of this thing here, ax squared plus bx plus c. If you calculate the coefficients a, b and c that pass through the 3 data points, you put that back into this integral, you do the integration, and it does seem rather remarkable that this should be the case, but it's true. The integral looks like that. h on 3 times the function value at x1 plus 4 times the function value of x2 plus the function value of x3. So we never actually need to know a, b and c. All of that stuff, all of this comes out in the wash and we get a really simple formula that looks like that. That's about the only thing you need to remember for Simpson's 1/3 rule. Now, plus the truncation error for one application goes like h to the 5th. That's a handy thing to remember as well. So another way to write Simpson's rule is actually in terms of the width of the interval. And so remember, got our functions doing this, and we've got 3 points. Typically that's called B and that's called A. That's H. And that's H. So, as I said before, B minus A is equal to twice H. You've just got to remember that H is not equal to B minus A. Or it's only equal to B minus A if you're considering the trapezoidal rule. Okay, for all other ones, it's some integer fraction of it. So looking at the integral like this, another way of thinking of it, well, it's equal to the mean width, which is that thing there, plus, not the mean width, sorry, the width, multiplied by some estimate of the average height in our domain. And the average height is given by this approximation here. It's not exact, but it's approximate. Just another way of thinking about the same thing. So, I think we recall the polynomial from the last lecture. It looked something like that, and we wanted to integrate using the trapezoidal rule, and these are our 2 endpoints, and we got some tiny little integral that looked like that, whereas the full integral was this whole thing here, and our error was about 90%. If we split it into 2 sections and used the composite trapezoidal rule, we got a better answer, but it was still significantly in error. So, we're going to integrate this from 0 to 0.8, like we did last time, but we're going to use Simpson's 1/3 rule, just one application of Simpson's 1/3 rule. So we're just going to split the domain into 2 parts. So we need 3 points, n is equal to 3. So therefore, the mesh spacing, or the spacing h, is equal to b minus a divided by n minus 1, which is 2, which is equal to 0.4. So our points are going to be 0, 0.4, 0.8. We're going to calculate the function at those 3 points. Okay, now I've already said that. So just need to put all these values into the rule. It's as simple as that. We know what the function values are. We've calculated what h is equal to. It's 0.4. So it's going to be 0.4 divided by 3 plus the function value at 0 plus 4 times the function value at the midpoint, which is 0.4, plus the function value at 0.8. You add those up, and you get that. We actually have an analytic result for this thing here, which is equal to 1.64053. If we use the 2-segment composite trapezoidal rule, we got something that was like that. So, in some sense, the 2-segment trapezoidal rule, you're using 3 points and fitting straight lines. Here, we're using the 3 points and fitting a parabola, and we can see that previously we got something that looked like that. Now previously got something that looked like 1.06, now we're getting something that looks like 1.4. So it's a significant improvement. Still using the same number of points, but instead of using straight lines, we're using one parabola. So it's more accurate for the same step size and the number of points. And that will almost always be the case. In rare cases it might not be, but it would be pretty unusual. So if we actually now look at this particular function and actually see what we're getting, those are the 3 points that we're looking into. Composite trapezoidal rule fits these 2 trapezoids. That one there and that one there. So we're missing out a bit there, but we're missing a whole lot up the top there. That's where a whole bunch of the error comes from. We're still missing a lot of this when we use Simpson's rule. So it's by no means doing a great job of the integral. In actual fact, that can clearly be seen by the fact that the error is still about 16%. But if we look at this function, it's got a couple of inflection points. There's a minima here, a maxima there, a local minima there, another maxima there. We can't expect to fit a quadratic neatly to that data. It's just not going to be possible. So we don't expect the answer to be good. But nevertheless, it still does a much better job than fitting two trapezoids. In fact, we've halved the error. Okay, I've basically said this before. The error goes like the fourth derivative of the function you're trying to integrate. So if that happens to be a cubic, you're going to fit it exactly. And it's going to look like that interval raised to the fifth power. Okay, now don't recall that that's also equal to h to the fifth on 32. Sorry, equal to 32 times h to the fifth. Okay. So, just like the trapezoidal rule, we don't actually have to fit use one pair of intervals. We can have 2 pairs of intervals, or 3 pairs of intervals, or 5 pairs, or 20 pairs of intervals. Okay? What that means, however, is there must be an odd number of points. Okay? So you've got to have 11, or 19, or 73 points to use Simpson's rule. And not only that, because of the fact that at least within each pair of intervals you need to have the same mesh spacing, that point actually has to be right in the middle, it really doesn't make much sense to use Simpson's rule with variable spacing, because you'd have to have that variable h in pairs. And all of a sudden you start doing that, it just starts looking really messy and it's very easy to make mistakes. So for Simpson's rules, you would always use equal spacing. Okay, trapezoidal rule you can get away without doing it, but for Simpson's rule you always use a constant h. Now, because of it's not heavy weighting, but it's non-uniform weighting of the internal points, the formula is just slightly more complex for Simpson's rule, but boy, it's not really very much more complex. So let's just have a look at the composite Simpson's rule. We have A and B. We split it up into pairs of intervals, and there's 5 pairs of intervals there. So we have 10 intervals, 11 points. And we look at the first interval, or first pair of intervals, I should say, from there to there. We fit the parabola to those 3 points. And the way in which we do the integral then is by taking 1 times the function value there, plus 4 times the function value there, plus 1 times the function value at the end. So we've now done the first pair of intervals. We then move on to the second pair of intervals. 1 times the function value here, 4 times the function value there, 1 times the function value there. Move on to the next pair of intervals, and so on. And what you can see is that these internal points here, they appear once in this sum and once in the next sum. So in actual fact, you want to include them twice in the total sum. Okay, so we've gone from 141 for this single application of Simpson's rule to something that, if we break this up into segments, go through it, something that looks like there's a 1, there's a 4, there's a 2, and then there's a 1. Okay, so again, the way in which we did the trapezoidal rule, we broke up one integral into a series of integrals, but now we're going from point x1 to x3, x3 to x5, etc. We're using each of those, splitting each of those out using Simpson's rule, adding them together, and the number of the multiplying factors outside each of the points go in a pattern 1, 4, 2, 4, 2, 4, 2, 4, 2, and finishing off with 4, 1. So that means that the first point and the last point have a 1, each of the even points have a 4, and each of the other odd points have a 2 multiplying factor out the front. So that is what we see down here. The integral is equal to h on 3, function value at 1, function value at n, plus 4 times the even points plus twice times the sum of the odd points. Is that kind of clear, that the way where that comes from? It's straightforward, and really the best thing to look at is just this figure here is the one that really helps clarify where that all comes from. So let's go back to the same polynomial we looked at just a minute ago. We looked at a single application of Simpson's 1/3 rule previously. We were able to reduce the error from 34% to 16%. Let's apply Simpson's rule twice. In other words, we want 2 pairs of segments or 5 points. So, function here, we're integrating again from 0 to 0.8. We need a spacing that's given by h is equal to 0.2. That's the distance divided by the number of intervals, which is 4. So our points are 0, 0.2, 0.4, 0.6 and 0.8. And we then, of course, need to calculate the function values at those 5 points. And this is the composite Simpson's rule. And I should say, you're not going to have to remember all of these formulas, although it's not a bad idea to do so. Plugging our numbers in here. So function value at 0, that's that point there. Function value at f8, that's that value there. Then the even points are the function value at 0.2 and the function value at 0.6. The odd points, function value at 0.4, just the function value at 0.4, there's only one of the odd points. They're multiplied by 4, those are multiplied by 2. You stick the numbers in, we now get a value that's 1.62. So if we compare that to the analytic result, we're actually doing really well. We've got the error down to about 1% just by splitting this interval into 4 subintervals and using Simpson's rule to integrate. So I think you can see that, okay, if you've got the error down from 16% to 1%, by halving it, if you halved it again, you'd probably get that 1% down to 0.02% or something like that. And then halve it again, you can see that the error rapidly drops off. So let's just have a look at what we're doing here. So this is Simpson's rule with 1 segment. This is Simpson's rule with 2. So 2 pairs of segments. So the first parabola is fitted between these 3 points. We can see, because there's an inflection here, the curve goes up and it comes down and then it goes up again, we're never going to fit a parabola to this bit in here. So we're always going to do quite badly down this bit, in this bit down here. But these 3 points are actually pretty nicely fitted by a single parabola. And that's where we've gained a huge amount of our accuracy, is by fitting this bit up here much, much better. And as the function gets more complex, you need to make the spacing smaller so you can capture those things reasonably well with a parabola. So we've gone from 16 down to 1. Okay, Simpson's 3/8 rule, it's not really a whole bunch different, except we've now got 4 segments. Ignore that figure for the moment. So what we're going to do, 4 points, 3 segments. Simpson's 3/8 rule corresponds to putting a cubic polynomial through the points. So we're going to fit something that looks like ax cubed plus bx squared plus cx plus d. And just like with the Simpson's 1/3 rule, we never need to know what these coefficients are. Okay? We calculate them, we put them into the integral, we do it analytically, we churn through the numbers, and the formula that pops out at the end is this one here. The integral is equal to 3/8, that's where Simpson's 3/8 rule comes from, 3/8 h times the function value, the first point, function value at the end point, plus 3 times the function values at the middle points, summed together. Again, it's a simple formula. This is the 1 interval case, and of course you can do the same thing as you did with Simpson's 1/3 rule, except now the number of segments that you have has got to be a factor of 3. You've got to have 3 segments, or 6 segments, or 9 segments, or 12 segments. So it becomes a little more clumsy than Simpson's 1/3 rule. And in actual fact, the thing about using Simpson's 3/8 rule is that it's not really any more accurate than Simpson's 1/3 rule. It is maybe just a little bit. But because of this clunkiness, or the fact you've got to have factors of 3 in the number of intervals, Typically, you would only use Simpson's 1/3/8 rule if you had an even number of points that you needed to integrate. And so, for example, in this case here, we've got 6 points. We'd use Simpson's 1/3 rule on this pair, and we'd use Simpson's 1/8 rule on the other 3. So you'd use the 1/3 rule for most of it, and just use the 3/8 rule just for the end. Now, are you ever really going to come into a situation where you really have to do this? It's probably moderately unlikely, because you can nearly always split things up into as many intervals as you want. Nevertheless, it's there and it's available, but it's not necessarily a whole bunch more accurate. So the error, again, looks like a fourth derivative term plus an h. That's equivalent to 32. Actually, it's not going to be 32 now. It's going to be 3 to the power 5 times h to the 5th, this term here. As I said, it's a little bit more accurate, but not really worth the extra effort. Okay, and again, you would only use it if you had to do it because you had an even number of points. So if we go through the same example we've had a look at already, use Simpson's 3/8 rule, we now need 3 segments and 4 points. Okay, so our mesh spacing now, it's a little bit more inconvenient for this example. It's 0.8 divided by 3. So the function values are going to be 0.2, 0.2, 0.2667, etc. I actually think 0.2667. Yeah, that's correct. We just substitute those function values into the formula. That's all you're doing. And again, if you calculate it, you get a value of 1.519. So that compares to about 1.60 something or other for 2 applications of Simpson's rule. So it's not as accurate. Okay, it's more accurate than one thing of Simpson's 1/3, but it's not better than a composite Simpson's. Okay, this is what I've been sort of going on about. If you've got 6 points and 5 segments, you combine Simpson's 1/3 and 3/8. So you still need you need 0.8. You need 6 points, so you need to divide 0.8 by 5 to get the mesh spacing h, or the spacing between the points, and that's equal to 0.16. So the function values now are going to be 0, 0.16, 0.32, 0.48, etc., which is what we see here. Calculate the function values then for this, this, and this. We use Simpson's 1/3. For this, and this, we use Simpson's 3/8, which looks like that. So that's from the first one, that's from the second one. We add them together, and we get that. So the analytic result was there, and we can see we've actually dropped the error quite significantly. We're down to 1/5, effectively 1/5 of 1% now. So that was down from 1% with 2 applications of Simpson's 1/3. So there is actually some advantage in doing that for these endpoints. You actually do get slightly better results. So those are Simpson's rules. They're very simple formula for doing an integral, and the key concept you have to remember is that what you are doing is you are fitting a polynomial to the points and analytically integrating that polynomial. You don't actually have to do any of that, because the actual rule itself tells you what the answer is. It's, in the case of Simpson's 1/3, it's just equal to function value at the left plus 4 times the function value at the middle plus 1 times the function value at the right. And similarly for the 3/8 rule. There are actually a number of other much more advanced methods for doing integration even than Simpson's rules. So let's just go back to the trapezoidal rule just for a minute. If we have some function that looks like that and we have function values here and here, the trapezoidal rule says, okay, let's draw a straight line between those 2 points and we're going to approximate this as the integral. And we can see here that we're not including any of that stuff up there, so there's going to be a big error. But what if we did things a little bit differently? We said, well, we're only going to use 2 points, but we're going to choose those 2 points not to be the end points, to be some other points. And there are very good ways of actually choosing those points. We're not going to go through it in this unit, but there are ways of saying, okay, let's choose this point and this point here. And let's then draw a straight line between those 2 points. And because our interval still goes from here to here, we need to make that straight line go over the points. past the point, sorry. And then let's approximate the integral as the area underneath this straight line here. So you can see what we're doing is we're overestimating the integral in these corner bits, but underestimating it here. And these two things cancel out to some extent. Never completely, but to some extent they cancel out. And in actual fact, you don't have to draw straight lines. You can draw all kinds of much higher order polynomials as well, but the basic underlying principle is the same. We don't choose the end points. We choose a special set of points which are called quadrature points. And those points have been chosen very, very deliberately to give you the best kind of properties. And you'll often hear that, or you will hear that in the future, the term Gaussian quadrature. That's exactly what you do in Gaussian quadrature. You choose the points where you want to calculate the function to give you the best possible outcome. And you don't always know that a priori. It will depend on the function, but in general they will give very good answers, much, much better answers. Okay, we've already talked about Simpson's rule requiring evenly spaced points, so that is a bit of a disadvantage. I mentioned before that function where you've got very sharp points like that, you'll need, if you want to get good results in this point here, you need to have very, very fine spacing to capture that. But if most of the function's not doing much, it's sort of sitting out here, behaving itself quite nicely, and there's only a really sharp peak right in the middle, if you want to use Simpson's rule, you've got to use a fine spacing everywhere, because h has to be the same. So Simpson's rule can be quite inefficient. Now, of course, one thing you could do is you could split up your domain into the bit where the function varies slowly and use a big spacing in Simpson's rule, a little bit in the middle where a function varies very rapidly and use fine spacing, and then a bit on the other end where it didn't do very much. But you'd need to know exactly where the function was behaving badly in order to do that. Sometimes you'll know that, and other times you'll have absolutely no idea when the function's behaving badly. There are a set of techniques called adaptive quadrature methods. They automatically adjust the segment width so that you only use the segments, small segments where you need to. We're not going to worry about those in this unit here, but they do exist. They are, of course, as you might expect, built into various different kind of MATLAB functions. So there's one function called quad, which uses adaptive Simpson quadrature. So it's Simpson's rule, but they do split the domain up into different bits and use different step sizes. And there's a function called quad L, which uses what's known as Lobato quadrature. You don't need to know what that is. It's designed for functions that are maybe smoothly varying, but you need to have very, very accurate results. And the syntax, the way in which you call that from MATLAB, is just like this. Quad and quad L, you pass in your function handle, the function you're trying to integrate, and you pass in the limits A and B. Okay? So what I suggest you can do in your labs, if you write a Simpson's rule integrator or a trapezoidal rule integrator or something like that, and you've got an answer out and you don't know whether it's correct or not, just whack your points into one of these functions here. These aren't going to be exact, but they're going to tell you whether you're close to the right answer or you're miles and miles away. Okay, so this is a useful check that's going to help you out. Okay, so what have we covered today? We've covered Simpson's 1/3 and 3/8 rule and the composite versions of those. We've also looked at combining the 1/3 and 3/8 rule when you have an even number of points. And we've had a very quick look at the MATLAB quadrature functions. So, that's it for today.